So today we're going to continue our discussion on domain and range, but instead of looking at a graph, we're going to look at an equation to come up with our domain and range. And kind of an oxymoron, because as I start here, my examples on the front page are graphs. But we'll get into the equations here in about 10 minutes or so. So we saw some of these types of graphs yesterday when we were working in our notes. And what we see in this problem is that this kind of function is a linear function. And the equation of the linear function, it's the parent function, it's the most basic of the lines, is y equals x. And in this particular case, just to digress for a moment, if you think back to slope-intercept form, our slope is up 1 over 1, up 1 over 1, up 1 over 1, and our y-intercept is 0. So for the video, if I start at 0 and I go up 1 and to the right 1, up 1 and to the right 1, that's where that slope comes from. But what's more important here for us is what's the domain of this? You remember from yesterday? I think she said it. Negative infinity to infinity. And not only is the domain of any linear function that, but the range is as well. And I actually need to stipulate that just a little bit more. Reminder that infinity always has a parenthesis when we're writing it in interval notation. But here's what I put in my notes, and that is that any line with a slant has domain and range of negative infinity to infinity. It needs to have a slant. Any line with a slant has domain and range of negative infinity to positive infinity. Our next function, we also happened to see something like this yesterday. And this kind of function, we called it a parabola yesterday, but it's also more specifically called the quadratic function. We will spend a whole unit on quadratics sometime this year, this school year. But a parent function, that's the most basic of the functions. Our parent function of a quadratic is y equals x squared. And the nice part here is that we have our graph, so we can identify what is the domain and what is the range. And just as an aside here, is this a function? Yes. Is it one-to-one? No, it's not one-to-one. But our domain, what we said yesterday, is that our domain of a quadratic, or a parabola here in this case, is negative infinity to infinity. Remember, our graph keeps going up, and as it goes up, it's going out as well. So we need to take into account all of the x values. But our range is not negative infinity to infinity. And what we oftentimes say with range is, do we have a high point or do we have a low point in the graph? And on this particular problem, we have a low point. That's the lowest point in our graph. That's where we're going to start in our range. But then our graph continues to be upward. So it's going to be 0 to infinity. And 0 is on the graph, so we're going to have a square bracket. Infinity always has a parenthesis. In terms of notes, what I wrote down in my notes is that, so for our notes, what I wrote, and again, these might be good notes for you and they might not be good notes for you, but for the range, ask, do we have a high point, or low point on the graph? And if the answer is yes, that can help us identify the domain, identify the range like it did on this particular problem. Do we have a high point or do we have a low point? We found the low point and we came up with 0 to infinity. We kept going on and on and on and on. But we did have a definite starting point, in this case a low point on the graph. The next one. We haven't necessarily seen a picture like this for a couple of weeks that I remember. Actually, we might have seen it in our practice. But this kind of function is a square root function. And I think that we will do at least a mini unit on graphing square root functions sometime this school year. I do want to make the picture just a little bit more specific. I want to put a point right there and an arrow there. But a square root function is y equals the square root of x.
How are we supposed to know if that function is in the test? If it's...
So now, when we take a look at this one, we have a starting point. And domain is dealing with the x values, the inputs. So in terms of our domain of this function, we're starting at 0. We're going to continue on forever towards the right, which is to infinity. And infinity always has a parenthesis. 0 is a value that is specifically on the graph. It's going to have a square parenthesis, square bracket. Well, the range is going to look remarkably similar because our starting point on this graph is 0, 0. It's the origin. And so we're going to start at 0, and then we're going to keep going up, which means that we're heading towards infinity. And again, that 0 is on the graph, so it's going to have a square bracket. I don't have any specific notes for this one. Is there something that you think we should add? Okay. When we look at the last type of function here, it's nice to have the picture. We deal more with this kind of function in college algebra and pre-calculus. But the kind of function that this is a rational function. And the parent function is y equals 1 over x. And our domain and range are going to be pretty weird here for a minute. But what happens on these graphs is that these graphs are getting closer and closer and closer to the x-axis, or they're getting closer and closer and closer to the y-axis, but they never quite touch the x-axis or the y-axis. So in terms of interval notation, what we would say is that we're going to go from negative infinity to 0, but 0 is where the x-axis would be, so it's not included. And then we're going to put a u, which stands for union or joins with. Then it would go from 0 to infinity. No bracket, because we're not going to touch the 0. We're not going to touch the x-axis. Same notation here for the range. It's going to be negative infinity to 0, joined with union, that's what the u is, 0 to infinity. But as you're writing that down, you're thinking, that's kind of complicated. And one thing that we're going to see as we flip over the paper is that it's probably going to be easier to use set notation with this kind of function, because that's pretty complicated right there. So if we turn our page over, from what we saw in the front, the first two weren't too bad. Linear and the quadratic, we're used to those. But we might worry about the other two, the square root function and the rational function. And like I say there in bold, sometimes it's better to use the set notation. Because when we do, it's already going to be in the format that we're looking for. We like interval notation, especially when we're dealing with graphs. But sometimes it's easier to use the set notation. So as we deal more specifically now with the square root and the rational functions, our first here, the square root functions, we need to watch out for a couple things when we're dealing with the square root function. We have to make sure when we're dealing with these that only positive numbers or 0 fall underneath the square root. We do not know how to take the square root of a negative number. And how we do this is, how do we find the domain from an equation then? Well, when we're dealing with positive or 0, we're going to take the value that's underneath the radical. Sometimes I call it the radicand, just so you know. And positive means greater than or equal to 0. The greater than is the positive, the equal to is the 0. We set it greater than or equal to 0. Then we solve our inequality. We add 6 to both sides. We get x is greater than or equal to 6. Lastly, we're going to put this in set builder notation. When we put it in set builder notation, I don't write it again. I take my answer right there, squiggly bracket, x bar, for all values of x such that x is greater than or equal to 6, squiggly bracket. There's set notation. And that's what we do when we're dealing with the square root function. When we look at the rational functions, same kind of thing we need to watch out. And what we need to watch out for is we need to make sure that 0 is never in the denominator. Of the fraction. The denominator, by the way, is the bottom of the fraction. And how we solve or how we find the domain of a rational function is we take the denominator, the bottom of the fraction, and we set it not equal to 0. Then we solve that, subtract 3 from both sides, and we get x doesn't equal negative 3. And let's put that in set builder notation, which again is squiggly bracket, x bar, squiggly bracket. Now just as an aside here, and I don't think you should write this down, this means negative infinity to -3 joined with -3 to infinity. So there's the complicated version of that. Isn't the way that we just came up with it much more understandable? X doesn't equal -3. A lot easier to deal with than this complicated here, which I'm going to scribble out. We're not dealing with range today, but when we are dealing with range, we're going to stick with using a graph for now. But our primary focus here to finish up is we want to find the domain. And the nice thing is, it's the same every single time, but you might have to memorize which one is which. So hopefully the practice will be enough, but that might be someplace where we need to sit down and really think about it to memorize it. But our first example here to find the domain of these functions, and we're going to leave them in set builder notation. Here's a rational. So we're going to take the bottom, the denominator, and we're going to set it not equal to 0. We're going to subtract 10 from both sides, and we get x doesn't equal -10. That's our domain, and we want to put this in set builder notation. Again, I don't write it over, I just put it the set builder in. Squiggly bracket, x bar, squiggly bracket. The denominator of the fraction is where we need to be concerned when we're dealing with the domain. So our next one, we take 3x minus 6, the denominator, the bottom of the fraction, set it not equal to 0. We add 6 to both sides, and we get 3x doesn't equal 6, and divide everything by 3. 3 times x, inverse operation is to divide, and we get x doesn't equal 2. Put it in interval notation. Sorry, not interval. In set builder. Squiggly bracket. X bar. Squiggly bracket. Letter C. Fraction. We need to be concerned with the denominator, the bottom of the fraction. We're going to take 5x plus 2 and set it not equal to 0. Solve that. Subtracting 2 from both sides. We get 5x doesn't equal -2. It's 5 times x. Our inverse operation is to divide by 5. And we end up with x doesn't equal -2/5. Put this in set builder to finish. Squiggly bracket. X bar, squiggly bracket. Again, probably thinking that it's not hard, but we need to know what to do when we see a fraction. And the same thing's going to happen. We need to know what to do when we've got a square root function. Well, it's the same setup every single time, which is to take what's underneath the radical and set it greater than or equal to 0 this time. And that's the part that you might need to memorize. What do you do when you have a fraction? What do you do when you've got a square root? Then we solve. We add 12 to both sides, and we end up with x is greater than or equal to 12. And we can finish by putting that answer in set builder notation. We don't need to write it down again. Just fill it in. Squiggly bracket, x bar. For all values of x such that x is greater than or equal to 12. And it's the same process here. The radicand, the value underneath the radical, has to be greater than or equal to 0. We have to be concerned about when, what's underneath the radical has to be positive, or it can be 0. We can't take the square root of a negative. So it's got to be greater than or equal to. We subtract 4 from both sides, and we end up with 3x is greater than or equal to negative 4. And then we're going to divide both sides by 3. And we end up with x is greater than or equal to negative 4/3. And then once we get the x is greater than or equal to negative 4/3, if you prefer x is greater than or equal to negative 1 1/3, put it in set notation. Squiggly bracket, x bar, squiggly bracket. And to finish, pay attention to this one. Make sure that you've got the right answer if you're working ahead. The value underneath the radical is still going to be set greater than or equal to 0. And just be careful, because I'm going to move the 8 over here to the right side. And we're left with negative 2x is greater than negative 8. Again, I prefer to keep my letter on the left, like we did with our inequalities earlier this week. But what happens to an inequality when we divide by a negative number? And what happens when we divide by a negative number is that the direction of our inequality changes. And now we can finish that problem. Negative 2 divided by negative 2 is x. Negative 8 divided by negative 2 is positive 4. But again, when we divide an inequality, when we divide both sides of an inequality by a negative, the direction of that symbol changes. And then I'm going to squeeze it in, squiggly bracket, x bar, squiggly bracket, for our set notation.